Hello, and a very warm welcome on behalf of NTI Audio. I guess you know the situation. You are in a conference call with several participants. You ask a question to the audience, and it takes a hell lot of time until you receive an answer. You are not sure whether the question has not been understood or there were other reasons. Well, one of the reasons that may occur is a high latency in the transmission, a high time delay between the input into the conference system and the return. And this is the topic we are talking about today, not only about conference systems, but also other applications where you are encountering latency. But let me please first introduce myself. My name is Markus Becker. I am moderating this webinar, and I'm assisted by Greg Schmiedle, our product manager, who is taking care of the incoming questions and comments. We have prepared the following topics for you. We start with an overlook on the motivation and the scope of this webinar. We will very briefly provide a definition of latency and introduce you to possible causes and effects. Then we will present a number of typical numbers of latency time for different applications, and we will also introduce you to the measurement concepts that are available. A major part of this webinar are 3 practical presentations that you will see consequently. After that, we will summarize the key points of this presentation and provide some additional hints and tips before we, at the very end, will take a look at the questions that have popped in and possibly add some comments. I expect that this webinar will last about half an hour. So when can we encounter latency? When can we get confronted to this effect? One example I have already given are conference calls, video conferences, webinars, whatever. Another case could be if you are using a wireless headset, there may be a noticeable delay between the audio that you are listening and the video that you're seeing in a video chat, for instance, which is also most probably due to a certain latency in one of these channels. Then a similar application, which is, however, still quite different, is the in-ear monitoring of musicians on the stage. You see this guy here has an in-ear monitor which provides him the feedback of the sound that he is singing and of his instrument, and we have some special requirements for these applications. I will come back to that later. And then we have a third case which is completely different. Here you see a huge crowd which are waiting or standing in front of a stage. The picture has been taken from that stage, and you, as the installation guy, for instance, you are responsible to provide a decent sound to these people, even if they are standing right back at the rear of this field. And a good sound includes not only a good sound quality, but also that the sound level is high enough and that everybody has the impression that the sound is coming from the stage. This is another application that I will explain in more detail during this webinar. Well, the definition of latency is quite simple. It's the time difference between the moment when a signal enters a system and the moment when it pops out of that system. So measuring this time delay corresponds to the latency. What can be the cause of latency? The first one is, of course, the signal runtime through the system. A typical example here is the sound propagation through air, which is limited, of course, by the speed of sound. So if you have a major distance between a loudspeaker and a listener, you will for sure notice a certain latency, a certain delay. Second possible cause is the digital signal processing of a signal, for instance, an analog digital or digital analog conversion. Any digital signal processing is related to a delay of the signal. So in other words, is causing a latency. And then as a third cause, we have the signal buffering, which is sometimes required, especially when we are dealing with long distance connections with long distance signal transmission. Here we need, for instance, the buffering for the error correction, or if we have interrupts on our connecting line, we need to compensate them because we want to make sure that the receiver still will receive the full information, and that is done by buffering, but any buffering will of course also add to the latency. Well, what are the possible effects of latency? One is a bad lip synchronization. If you look at this guy, he is certainly not saying in this moment. So there is apparently a latency of the audio signal compared to the picture. We may have annoying delay of the feedback coming back to the initial picture with the conference call, where there is a long delay between the question and the answer due to a long signal runtime. That can be an effect, or even a misguided perception of a sound direction. So you're perceiving that the sound is coming from the left, although in reality it's coming from a different direction. I will come back to that later. What are typical latencies in reality? When we talk about an online conference or a webinar, in best case, we are talking about few milliseconds latency, but this can go up to even several seconds. And even worse, this value can vary over time. So you may have a low latency in the beginning, growing over time, or back and forth, whatever. Another example are the very popular Bluetooth headsets. Here, the latency depends strongly on the protocol, the type of Bluetooth connection. There are different profiles, actually, Bluetooth profiles defined. Here we show you the three examples with three different latencies. The aptX-LL has a latency of below 40 milliseconds, while the A2DP is in the range of 200 milliseconds. The differences are mainly due to the different codecs that stand behind these profiles. And then, as stated before, which is this is a completely different application, although it looks quite similar, the in-ear monitor systems for stage musicians. Here we have a pretty strict requirement that the latency should be as small as possible. And the reason is quite obvious, because when you are singing into a microphone and you hear your own voice over the in-ear monitor, you could not accept a major difference, because this would completely puzzle you. It is not feasible to make a decent performance with high latency in that in-ear monitor, so that shall be as small as possible. The shortest latency here are the analog systems. The digital in-ear monitors feature something below 5 milliseconds of latency, which of course is nothing to do with the Bluetooth. It's a completely different technology. And when we are using a stage monitor, we have, in addition to the electric latency, also the propagation time from the sound from that stage monitor to your ear. The goal is always to stay below 10 milliseconds. And last but not least, we have a special case. I already mentioned that shortly, the support loudspeakers for big venues. Here we have to adjust the latency for certain reasons, which I'm going to present to you. And we are talking here about some 10 milliseconds up to few hundred milliseconds. That depends strongly on the dimensions of the setup. So let us take a little bit a closer look on this case. We have a large field with lots of people standing around the audience who are looking for the presentation on the stage here. We have stage loudspeakers, and let's assume you are responsible for the sound. So you want to make sure not only that the quality is good, but that also everybody here in this field receives a decent level of sound. So if we look at this person here at the very end of the field, if we want to provide a decent sound level here, we would need to pimp up the volume of these stage loudspeakers tremendously, which puts these people in front here pretty much in danger because the sound level would be certainly too high. So a solution for that is to introduce more loudspeakers, the so-called support loudspeakers in the middle of the field or even at several positions here in the field. So that allows you to apply a decent sound level here in the front and another good level here in the rear part of your field. However, we are now facing a new challenge, because if we look at this person here, he is exposed quite directly to the sound from this loudspeaker. So he will most probably see everything which is going on the stage, but he will get the impression that the sound is coming from the right-hand side. And this is not what he's looking for. He wants, of course, to get the impression that both what he sees and the sound is coming from the stage. Well, the solution to this challenge is the use of the so-called Haas effect. And the Haas effect says that the first sound wave which comes to the ear of this person will give you the direction, the perceived direction from the sound. So if we succeed to get the sound coming from the stage speakers first to this person, then we will have good chances that he will be happy with the setup. How do we get there? So the first thing we have to do, we have to measure the delay, the latency from the signal from this stage loudspeaker to his ear. This is the time t that we are measuring. And then we apply deliberately a delay to this electric signal that is provided to this support loudspeaker. And this delay can be adjusted to the propagation time t that we have measured, plus around 15 milliseconds. We have a certain tolerance here. It can be 10 milliseconds and can go up to 40 milliseconds. It is only important that the sound coming from the stage loudspeaker arrives here after the same sound which is coming from the stage loudspeaker. And then we get the impression that everything is coming here from the front. So how do we measure the latency or the signal delay? We have two possibilities, two options. The first one is what we call the open loop measurement. For this, we need a separate sender and receiver, a signal generator and an analyzer. We synchronize these two instruments. And then we can start the measurement by feeding the generator signal into a loudspeaker, moving the analyzer to the position where we want to measure, and then we will see on the display the result, the time delay of this signal. When we are using an XL2 analyzer, we can use the internal microphone for this measurement, and the display will show us the corresponding result. So we need MR signal generator, MR Pro or MR2. We need the XL2 acoustic analyzer. We can cover up to 1 second with this measurement, and we have a resolution of 0.1 milliseconds. It's quite accurate, actually. There's a second option to measure the latency, and that is what we call the closed loop approach. So here we are using one instrument to send out the test signal, transmit it through our system, receive it back, and then calculate the latency. It is actually a correlation analysis. What we do in the instrument, we calculate the impulse response of this light sweep burst. Please, this picture is only schematic. In reality, it looks a little bit different, but for better understanding, I decided to choose this waveform. So we are calculating the impulse response from the generated signal and the received signal, and then we can very easily measure the time difference, which is the latency of our system. So we need an FX100 audio analyzer as an example. We have a range of up to 19 seconds for that measurement and a very high resolution of down to 0.05 milliseconds, depending on the bandwidth of our device under test. Well, so let us take a concrete look at these setups, these measurements, and we are entering now the practical presentation. The first part will be the open loop measurement with an EMMA Pro and an XL2. Both instruments are connected via USB to my PC, so you will be able to see the content of the screens of these instruments. We have a loudspeaker connected to the EMMA Pro, and in between an instrument which allows me to adjust the delay, to add a delay to that signal transmission. And I can also show you that with my webcam just for a moment. Yeah, here we are. You see here in the background, I have a loudspeaker. Here I have my XL2 instrument, behind that my EMMA Pro, and the device that allows me to add a delay. So I switch back to my screen. And to the screen content of the EMMA Pro and the XL2. So the first step, you remember, was to synchronize both instruments. For that purpose, I connect the EMMA Pro via a cable to the XL2. And as soon as I unmute my EMMA Pro, you will see down here, the XL2 will realize the incoming signal and will start synchronizing. So this is happening now. Takes very short time, and we are ready to measure. So we have 5 minutes time now to measure the delay. So I reconnect my EMMA Pro to the loudspeaker and start the measurement. You can see we have a result of 111.2 milliseconds. And if I move my XL2 instrument towards the loudspeaker, this number goes down. If I move it away from it, it goes up. By the way, you can also see the corresponding distance between the XL2 and the loudspeaker. And maybe now you ask yourself, why can that be 38.4 meter? The reason is because I have this delay instrument between the EMMA Pro and the loudspeaker. Now let us assume that we are right now measuring a support loudspeaker and we want to adjust the delay. We want to add more delay to come into the range we are looking for. For that purpose, we move the cursor here to the store. We save the current measurement result, and now by turning the potentiometer of my delay instrument, I can add the 15 milliseconds or whatever I want in order to get to the point where I want to be. So it doesn't have to be exactly 15 milliseconds. It's something around that, maybe a little bit more. Yeah. So this would be my setting that I'm looking for. Here you see the actual, the new measurement time, the new latency, that was the initial one, and the difference is the one that I have added with my instrument. So that was the open loop measurement for support loudspeakers. Let us go now a step further to the next presentation. This is the measurement of the latency of a Bluetooth earbud, a Bluetooth headset. I have here again the FX100 analyzer. I have a Bluetooth test box. By the way, if you want to know more about Bluetooth testing, we recently had a webinar on that topic, and you will find that video on our website as well. In addition, I have connected my FX100 to a reference loudspeaker, and here I have a test jig for my Bluetooth headset with a built-in microphone that is connected to the FX. So let me swap over to the software. Here you see again the wiring, the FX100, here connection to the loudspeaker, small loudspeaker in the headset and the Bluetooth device. This is the measuring microphone connected to the FX100. I have a reference loudspeaker connected to the instrument, and this is the microphone of the headset, which is fed back to the FX100 for the measurement. So here we have the worksheet where the measurements are executed. We have prepared a sequence, and I will start that right now. So the sequence asks me to connect my headset to the Bluetooth box via the HFP profile. I have already done that, so I can start. Maybe you heard that in the background. We have a delay of 78 milliseconds between the microphone of the headset, and we have a latency of 46 or 47 milliseconds of the loudspeaker of the headset. So two different latencies, one for the microphone, one for the loudspeaker. Now let us repeat the same measurement with another profile, and the system asks me here now to activate the A2DP profile. I'm gonna do that, so I disconnect my Bluetooth device. I select another profile, the A2DP, and I reconnect. The A2DP profile has been developed for maximum, for higher quality, better quality of the transmitted sound. We are reconnected, so let us see what is the impact of this higher sound quality. This, sorry, now I lost my connection. Let's try it again. But yeah, give me some seconds to readjust that. I think I have to terminate that briefly. Just a second. Let's try to reconnect our headset to the Bluetooth box with the A2DP profile. Yeah, this is unfortunate. I have a kind of a presentation effect. I guess you know that. Every time when you want to show something, it's going wrong. But let's give me a try to reconnect. Execute another scan. There it is. Connect. Okay, confirm. Yeah, and here's the result. So here we have only the loudspeaker in the headset that we can measure because the A2DP profile does not support a microphone connection, but you can see immediately that we have a much higher latency, 200 milliseconds compared to 47 in the HFP profile. So here you see directly the impact of a different codec, of a different type of signal processing in our device. Now let me also show you a third application, a third presentation, and that is the delay, the latency of this webinar connection. So how much time does it take from my spoken word to the moment when it arrives in your ear? For this purpose, we are connecting again the FX100 with the reference speaker. We are using my headset as the microphone. The signal will be fed to the PC and via the internet to a laptop computer, and from there back to the FX100. That allows us to determine the latency of this connection. So I switch back to the FX control software. I select the corresponding project. So all I have to do, I have to hold my microphone close to the reference speaker and start the measurement. And here you see the result. It's approximately half a second. That is the latency of our current connection. So let me get back to the presentation and summarize the key points that I have mentioned. The first one is, where does latency come from? It can be caused by the signal transmission channel, be it the physical runtime, as stated before, the sound propagation through air, the speed of sound, or the buffering in order to correct errors or to compensate a channel overload. Another potential cause of latency are the inherent characteristics of the signal processing, the digital signal processing, for instance, the Bluetooth codec, as I have shown you in my practical presentation. And a third cause can be a deliberate signal delay, as I showed you and explained to you for the support loudspeakers. How can we measure it? We can use the open loop approach with a generator and an analyzer being separated from each other, which we need to synchronize first, but then we can do the measurement, and the closed loop measurement, where the generator and the analyzer are within the same test instrument. Well, maybe now you ask yourself, what can we do when we are encountering latency, annoying latency? Is there anything we can do about it, what we can improve? Well, the answer is unfortunately not very optimistic, because in most cases, there's not much to do about it. Nevertheless, there is a certain chance sometimes you can optimize the system by adjusting some settings. I give you one example. We have some video players which allow to add a certain delay on the audio or the video channel if we have a gap in between, if we have a bad synchronization between the audio channel and the video channel. So some video players allow to compensate for that gap in order to minimize the latency. Another approach would be to swap to another technology. I gave you one example, in-ear monitors, stage monitors. Analog technology is much faster than digital technology, so that may be a potential solution, or as shown before, talking about Bluetooth connections, by choosing another profile, this may help to improve the situation. However, in most cases, especially signal transmission via the internet, the chances that you have, the means that you have, are quite limited or even non-existent. Well, I'm at the end of my presentation. From my side, I want to thank you very much for your attention. I hope I was able to answer most of your questions, and I would, of course, be very happy to welcome you at one of our future webinars. Up to then, have a good time and stay healthy. Bye-bye.